We're going to finish up our last notes about the nucleus of atoms with these notes called nuclear reactions. Our first question is, how are nuclear processes written? And the answer is as what we call nuclear reactions. Now, reactions are often abbreviated RxNS. So you'll see in the future that when I say reactions, it'll probably just be RxNS. Alright, so our first example is technetium 100, which is an element on the periodic table. It has 43 protons, and its mass number is 100. So technetium is going to undergo what is called alpha decay. Alright, so let's take a look and see. So the nuclear reaction for the alpha decay of technetium 100 is technetium 100. So remember, this is the isotope symbol right here for technetium. So the 100 is the mass, the 43 is the protons, and the Tc is the element symbol. Alright, so this atom, its nucleus, is going to fall apart. It's going to decay because the nucleus is unstable. It probably has way too many neutrons to proton ratio. So in order for it to become more stable, it's going to go through what's called alpha decay, and it's going to make a new element. We see here Nb. Okay, so it's going to make a new element, and it's going to spit out this alpha particle, He, okay, which is basically a helium nucleus. It's got 2 protons and 2 neutrons because the mass is 4. Okay, so this is how nuclear processes are written in these types of what we call nuclear reactions. All right, here's a second example. This is an example of carbon-14, so carbon with a mass of 14, undergoing what's called beta decay. All right, it's a different kind of radioactive process or nuclear reaction, and here again we've got carbon-14 to start with, so its mass is 14 and it's got 6 protons. And it's undergoing what's called beta decay, which I'll talk about all of the alpha and beta and stuff like that in just a few minutes. But in this case, we're ending up with a new element, all right, and we're spitting out something from the nucleus, all right. And in this case, it's called a beta particle. But in every single nuclear process, we're always making a new element. Okay, because we're changing what's inside the nucleus. We're either going to be losing protons and neutrons, or we're just going to be losing electrons. So we'll see how that works. In either case, though, it's important to notice that nuclear equations, when we're doing this math, they must be balanced in both the mass number, which is the top numbers, and the atomic number. So if we look at the carbon one again, we're going to see that if we treat the arrow as an equal sign, okay, the top numbers have to equal each other and the bottom numbers have to equal each other. So 14 plus 0 equals 14, right? And 7 plus a -1 equals 6. All right, the same thing works up here in the technetium one, where we have 100 as the mass, and that's going to equal 96 plus 4. Alright, so it's an easy way to figure it out. And then on the bottom, 43 is the total, and so over here we have 41 plus 2. Okay, so that's super important to realize in these nuclear reactions. Okay, let's take a look at our second question, which entails all of the different types of nuclear processes that we're going to study. Alright, our second question is, what are the types of nuclear processes? So we're going to start with the nuclear process of alpha decay. Alright, so in alpha decay, what happens is that the nucleus of an atom is unstable. So it's an isotope that has way too many protons way too many neutrons than protons, and so it becomes unstable and it starts to freak out. Okay, so in alpha decay, what the nucleus does in order to, calm itself down in a sense, is that the nucleus of the atom releases what's called a helium nucleus, basically, so that's helium, basically 2 protons and 2 neutrons. Okay, and this helium nucleus is what we call an alpha particle, and alpha particles are usually symbolized by the Greek letter A, or alpha. Okay, And so an alpha particle, again, is a helium nucleus, so you'll either see it as an alpha particle, like the alpha A, or you'll see it as an He and a 4 and 2, okay, to represent those 2 protons and 2 neutrons. All right, so the nucleus lets off this helium nucleus, 2 protons and 2 neutrons, and what we end up with is a brand spanking new element. Okay, we always get a new element in nuclear processes, and this element is going to have a smaller nucleus since we just let out 2 protons and 2 neutrons. In last class, if we had time for it, or in tomorrow's class, we're going to play a little game where you're going to be moving around across the periodic table, and you're going to be doing some nuclear processes. Well, in an alpha decay, you're always going to go 2 spots back on the periodic table. So you'll see that, or you have seen that on the game. So alpha decay always goes back 2 spots on the periodic table, and then so wherever you land those 2 spots back, that is your new element. All right, in alpha decay, we also have gamma rays, that third type of radiation, the most penetrating type of radiation, those high energy, also being released as well, okay, in alpha decay. So let's take a look at an example of an alpha decay nuclear reaction. So let's do uranium-238. Okay, that's a very popular one in nuclear processes, in nuclear power plants and such. So we've got uranium U, the mass is 238, and the number of protons is 92. Okay, so that's what we start out with. You can see here that we've got way more neutrons than protons, so it's going to be unstable. So in order for this atom to become more stable, it's going to let off a helium nucleus. All right, so that's our alpha particle. So we're going to have a helium nucleus get let off, which is 4 and 2. Okay, and so remember from what I said earlier in math, that we need to have the top numbers be equal on both sides of this arrow. So if we think of the arrow as an equal sign, the top numbers have to be equal, and those bottom numbers also have to be equal. Okay, so if we're trying to figure out what this new element is going to be after this alpha particle has been spit out, we just take a look at our periodic table. Okay, we can find uranium down at the very bottom in the lanthanide, anthanide, actinide series, and we can go back 2 spots on that from uranium. So in this case, 2 spots back from uranium is an element called thorium, Th. All right, and we can see that the Th is going to have 90 protons, right? Because according to our equation, we needed equal 92, so 2 plus 90 is 92. All right, and then for the mass number, it's going to be 234. Okay, because again, we have to have that top number, those top numbers equal on both sides of this addition problem. So 234 plus 4 equals 238. All right, our next type of nuclear process that we're going to talk about is beta decay. Okay, so beta decay is where an unstable nucleus, okay, one of the neutrons inside the unstable nucleus splits into an electron and a proton, okay, which is kind of weird to think about. But if you take an electron and a proton and you put them together, you get a neutron, right? Negative plus a positive come together, make neutral. Makes sense. Okay, so in beta decay, a neutron splits into an electron and a proton, and what the nucleus does is that it releases that electron. Okay, so we're going to get that electron being spit out. So that's what we call a beta particle. All right, and beta particles are usually either symbolized as the Greek beta symbol with basically a B with a long tail, or another way we can represent it is because it's an electron, we'll put a little e, All right, remember electrons have no mass, so they're going to have a 0 on top for mass. And it's basically an opposite of a proton. So we're going to put a -1 down here for the number of protons because it's opposite of a proton. So that's what we call a beta particle. Just like in in alpha decay, beta decay also makes a new element. All right, so remember, every time we have a nuclear process, we're going to make a new element. So in this case, the new element is going to have the same mass, right? Because remember, the mass of an electron is 0. So you're not losing any mass, but you will gain 1 proton. And it's kind of weird to think about, but when we get that neutron splitting up into a proton and a electron, that electron gets spit out, but now we've got this, proton, this new proton left over. So we're going to have 1 more proton. So when we think about it on the periodic table and in the game that we played, we're going to go, anytime we have a beta decay, we're actually going to go forward 1 spot on the periodic table. Okay, so beta decay, you go forward 1 spot. Alpha decay, you go 2 spots back. All right, and then just like in all types of radiation or radioactive decay, we're going to have gamma rays also being released. All right, let's take a look at one example for beta decay. Here we've got barium 140. So barium has a mass of 140 and it's got 56 protons. All right, and this is going to go through beta decay, which means that one of the neutrons in the nucleus is going to break down into a proton and electron, and that electron is going to get spit out. Okay, so we have no mass electron that is opposite of a proton. So we get the E with the 0 mass and the -1 on the bottom. All right, so if we take a look at the periodic table, again, remember we're going forward 1 spot on the periodic table. So forward 1 spot is lanthanum, which is La. Okay, and remember, in order, we can very easily figure out the numbers for lanthanum because, 56 plus a -1 is going to be 57. Okay. Actually, 57 plus a -1 is going to be 56. And then since we're losing no mass, okay, lanthanum will also have a mass of 140. All right, so that's a beta decay, okay, of barium. Once again, we get no mass being lost because we start out with 40. We have no mass being lost, so we end up with 140. And then the number, remember the proton number on the bottom also has to be equal on both sides of that arrow. So 57 plus a -1 equals 56. All right, we have 2 more nuclear processes that we're going to talk about, and they're much shorter. The first one is nuclear fusion. Fusion is anytime you fuse 2 things together, you join them together. So nuclear fusion is the joining together of 2 nuclei. Now this requires lots and lots and lots of energy input, and it also releases lots of energy as an output. So if you've ever heard of nuclear accelerators, they are basically huge machines. I'm not kidding, like miles long machines that take nuclear particles like protons and accelerate them with using high energy acceleration, and so that they can smash the protons together to fuse them together to make new atoms in the end. Okay, so nuclear fusion takes a lot of energy. It also gives off a lot of energy. So let's take a look at an example of nuclear fusion. All right, one example we can do is the fusion of chromium. Okay, Cr, chromium 52 is his mass, and he's got 24 protons. And we're going to fuse him with a helium atom. Okay, so helium atom has 2 protons, 2 neutrons, so it's got a mass of 4. Okay, and so what we're going to get, we can actually even, we can know exactly what element it is by looking at the numbers up on top, because remember that it's just very simple math. So 52 plus 4, right, is going to be, what, 56? Okay, so the mass of our new element is going to be 56, and we know that 24 plus 2 is 26. So our new element has to have 26 protons. So when we look at our periodic table for number 26, we can see that it's going to be iron, Fe. Okay, so as one way to make iron molecules is to fuse chromium atom and a helium atom together to make an iron atom. All right, so that's an example of nuclear fusion. All right, our last one is the opposite of nuclear fusion. It's called nuclear fission. So in nuclear fusion, we join together two nuclei. In nuclear fission, we have a nucleus breaking apart into smaller nuclei. So again, it's going to require lots of energy input, but even greater energy output. Because remember, nuclear fission is basically how atomic bombs and nuclear bombs work. So there's high energy input, but even greater energy output. All right, so let's take a look at an example of nuclear fission. Now this one is a little harder to predict. So when we're predicting things in class, it'll usually just be nuclear fusion or alpha decay or beta decay. Or you might have to fill in a missing piece of fission. So let's kind of take a look and see. So an example of nuclear fission would be, let's take uranium-235. Okay, so we have uranium-235. Uranium has 92 protons, and the mass is 235. Now, fission means that it's going to break apart. And one of the things that, or two of the nuclei that can happen when you break apart uranium-235 is that it can make barium-141. Okay, so barium-141 plus krypton, okay, which is 92, krypton-92. So krypton, all right, has, and the number of protons is 36. Okay, so krypton 92, and barium-141. And we also get a couple of neutrons spit out there as well. So we have two, basically neutrons, where we've got one mass and 0 proton count. Okay, so again, this is a little bit more difficult. We won't have any of them that you actually have to, predict, like, do the alpha decay for this. You're not going to be given, a question like, do the nuclear fission for this. But you might have to, fill in the blanks here with one of the elements that might be missing in a nuclear fission equation. All right, so that's all of the notes for this nuclear reactions one. So make sure you go through and make sure you understand the math behind it. It's very simple addition or subtraction math, and how to figure out, which elements there are on the periodic table. All right, we'll see you tomorrow.